Hopefully I remember to put everything on Piazza or Canvas or whatever it is that we're using. Right, nice to see everybody. The 4 of you that we have left. I guess as we get closer and closer to finals, there's usually exponential decay of people that show up in lecture, but we're used to that. In terms of announcements, your last homework is due tomorrow? Next week? Thursday? Whatever's on the sheet, do whatever's written down. Your homework's due soon. You should really consider finishing it. Thursday. Okay, fantastic. I love that for you. Yeah. So let's see. So your homework is due Thursday. I guess. Oh, that means you're not going to leave me alone in my office hours, huh? That's fine. I look forward to the company tomorrow morning. I may, as a warning before I forget, I may need to move the second hour of my office hours an hour later. Or the first, I forget, one of those two. MIT scheduled something tomorrow morning that apparently is mandatory, and now I need to adjust. So anyway, don't let me forget, and I'll look that up at the end of class. Beyond that, your only responsibility is the final exam, and lucky for you, MIT has scheduled it as late as possible, so you have plenty of time to study, is the positive spin to put on it, not that it's ruining your and your instructor's holiday break. But in any event, we'll help you prepare for that. We can hold office hours in the week in between in case that's a useful thing. Yeah, oh yeah, and I think I got the email from the university that we're supposed to encourage you to fill out your course reviews. Of course, that is indeed the case. You know, this is, as I'm sure you know, this is a new offering here at MIT and ECS, so your feedback is valuable, and of course, if you want courses like this to exist, you need to tell the department that, right? If you don't, then like they die. So anyway, that's that. Any questions about logistical stuff? Nope. Cool. All right. So in that case, we are going to continue our discussion of numerical methods by a topic which will either be the last or the second to last topic of this course. I haven't decided yet. Depends how slowly I speak in the next lecture or two. And that is ordinary differential equations, or ODEs. If I recall, ODEs are not a mandatory part of MIT's undergrad curriculum, which I find to be non-standard for engineers. So just out of curiosity, have we taken an ODE course? I'll cover the basics, but at some point in your lives? Yeah, about 50-50. Okay, no problem. Just useful for me to know. Have we taken a physics class that includes F equals ma? Okay, so we've at least seen one ODE somewhere in our life, which is a good start. Which is cool, because like the main application of most of this stuff is literally that one ODE. Okay, fantastic. So the theme of the last couple weeks of this course, in case we somehow missed it, is that we're optimizing for an entire function f rather than just a value, right? That's sort of the conceit to the last little bit of this course. And now the new twist is that we're looking for certain properties of f in terms of its derivative and then trying to infer f itself. So for example, in f equals ma, right, we know something about its derivative, like the acceleration of a function, and now we're trying to construct f from that, right? That's a very typical ordinary differential equation. And of course, there are many applications that fall into this bucket. Like, for example, products about approximating a function f, making it smoother, simulating some dynamical or physical relationship, kind of combining properties of two functions. So, for example, you see this in image processing a lot. These are very, very common problems, and we're going to go through quite a few examples. I'm thinking for our last lecture, maybe what we'll do is cover in a little bit of detail this neural ODE piece of research, which is really popular these days. It won the Best Paper Award at NeurIPS a couple years ago, to give you a flavor of where this stuff shows up in machine learning as well, rather than just solving a bunch of Newtonian physics problems, which is what people typically do in a class like this. So, in case you've missed it, essentially, the kind of problem we're going to solve is what we'll call an initial value problem, or IVP. There's already a typo, because f usually just goes from r plus to rn. Because we just predict the future, we don't have to predict the past. But the basic point is this, and I feel like this is like one of these things that's like needlessly heavy mathematical notation, but you're actually all quite familiar with it. Like it just looks kind of scary when you write it in this form. But the basic idea here, and it took me, by the way, until like very late in my career to kind of get comfortable with this kind of thing, which is even more common in partial differential equation. There's some unknown function f, and I have a relationship between f and all of its derivatives in time. And then basically I'm trying to find an f that satisfies those constraints. Right? So for example, in f equals ma, right, a is the second derivative of my unknown function. And I know the forces, I know the masses, and I'm trying to integrate to get the position as a function of time. Or let's do a second example. So let's say that I have a function y of t, and what I know is that y of t has this funny property that y double prime equals t y prime cosine of y. Why why, you might ask? I don't know. That's the first one that came up when I decided to write down an ODE. Although I believe, yeah, this should have a solution. Okay, so in any event, if you're curious, you want to write it in the notation above, how could we do that? Well, the first thing, of course, we could subtract y double prime from both sides. So we have t y prime cosine y prime minus y double prime, like that. And so from here, it's pretty easy to see that our function f of maybe, what, t, a, b, c? Right, so f is a function that takes in 4 inputs, and it's basically giving us this relationship when we plug in t, y, y prime, y double prime, right? So from this perspective, this notation is nothing more than t. I guess that should be a t. We got a b cosine a minus c, right? Just to kind of see how to convert into the notation of the problem here. So everybody see, this is actually not so scary, that what's on the slide here. This is just a complicated way of posing an initial value problem for ODE. Now, one thing you might notice, this is a bit of a strange thing. I mean, I think we're typically used to the situation where somebody gives us an ODE in the form of like y, like the highest derivative is kind of isolated on one side of the equation. You know, like y double prime equals all this stuff in terms of low order derivatives. But generically, that doesn't have to be the case. I mean, like this is a perfectly reasonable initial value problem. The other question I should ask is, why is it an initial value problem? What's this terminology? Yeah, I'm given f and all of its derivatives at time 0, and then my job is to integrate it forward in time. Yeah. Okay. And of course, the most famous example is Newton's second law. I'm glad I put it on the slide because I can never remember which Newton's law is which. But it's nothing more than F equals ma, right? So F is like the forces on your physical system, which are typically functions of positions and maybe velocities, right? M is mass, A is acceleration. Do we need to do an example, or can we all agree that this is indeed a reasonable ordinary differential equation we all want to solve? I think we all can. This is actually, MIT requires what, 801, so in principle, you're all experts on this equation. But there are many other ODEs as well. Actually, one thing to note is that like this feels like somehow the easy case. Like, oh yeah, this is classical physics. But actually resolving it and solving this equation is enough to make for entire courses worth of ODE solvers. And really diving into this stuff in detail takes a lot of time. If you're looking for a really famous example why this is hard, the place I would look is in protein folding. Here's the sort of typical energy landscape for a protein folding problem projected onto 2 dimensions, according to Science Daily magazine. So this is obviously a pictorial representation. But here's the basic idea. When I'm simulating a lot of these kind of atom or molecular models, you oftentimes run into really nasty ordinary differential equations that are nothing more than F equals ma at some macro scale, right? Like the forces in between the molecules that want to keep them at a certain distance apart, or the atoms. But essentially, what ends up happening is protein folding on the time scale of like atom motion is very long. But it takes a really long time for a protein to take a particular conformation and fold into a shape, relative to like vibrations of individual atoms, right? And so essentially, the forces that keep together a giant molecule like a protein are happening at all kinds of different time scales. Like on the tiny time scales, there's like the different subunits of these things that maybe are vibrating at some little tiny scale at a very rapid rate. And then over a much longer period of time, this thing is slowly taking some other conformation that has to do with like the larger scale configuration of all the atoms. Now here's the annoying thing about protein folding and ODE solvers more generically, is that the time scale that then you need to resolve the motion is whatever the smallest thing is in the entire system for a lot of the integrators we'll talk about today, meaning that the computational expense for simulating one of these things is enormously huge, right? If you just like write down all the forces that keep a bunch of atoms together and you want to figure out how a protein folds, this is an almost computationally intractable problem, which is why people have thrown all kinds of interesting and bizarre solutions to it over the years, even though at the end of the day, it's nothing more than F equals ma. I mean, like, in principle, you could use any of the solvers we'll talk about today. It would just take like bajillions, gajillions of time steps to do it in an accurate fashion. For example, I mean, what are some of the crazy ways that people have tried to solve equilibrium versions of this ODE before? When I was in grad school, the popular thing to do was to turn it into a video game. You guys remember this thing, this folding at home game where people would like use their Nintendo controllers and try to guess interesting low energy configurations of a protein? These days, I think that's largely been replaced by machine learning. But anyway, these are, like, we all know the physics underneath this. Like, this is not like, you know, quarks or some weird corner of physics that's unverified. This is like physics that we're pretty sure is correct. We just really still can't resolve it numerically, which is what's forcing people to use all kinds of creative tools. For very different applications of ordinary differential equations, another place you might look is gradient descent. So, unfortunately, you thought we were escaping our optimization chapter of this course, but actually, every single numerical integrator we will talk about in lecture today can be converted into an algorithm for optimization. And here's how we can do it. So, here's our favorite algorithm for optimization, right? This is the one that I think is simplest, where we have an iteration where we take xi, we subtract off the gradient of our objective function. I guess I called it e here, of xi, like that. Maybe multiplied by a step h. Hopefully this is a familiar algorithm by now. You've all suffered through it on your homework. Now let me rearrange this expression ever so slightly, right? So I could basically write this in an equivalent fashion as xi plus 1 minus xi over h. What is this equal to? It's equal to minus grad e at xi, which we're going to recognize in a few minutes as something we'll call a forward Euler integrator. If you haven't heard of that before, that's okay. But here's the sort of model that people can take that link these two areas of math together. Let's say that I kind of think of xi as roughly equal to some function which is equal to x at a time that evaluates, which is like I times h. So I'm like kind of marching forward time in increments of period h. Does that make sense? Then what is this thing? Well, we actually talked about it, what, 2 lectures ago? Previous lecture? Previous lecture. This is a divided difference, right? This thing kind of looks like maybe, I don't know, dx dt evaluated at time, I guess, maybe IH. Yeah, right? So at the end of the day, here's an ordinary differential equation model, which it's kind of simulating what gradient descent does in some version of a continuum, which is as follows: x prime equals minus grad e of x. This is a first order ODE. Okay? And it turns out that the behavior of this thing kind of correlates with the behavior of when gradient descent performs well or performs poorly. In fact, you can show that this ODE converges to local optima of E under certain conditions, which is kind of unsurprising. In fact, one argument basically takes conversion of gradient descent and then like takes a careful limit. Right? Yeah, and in fact, here's kind of a funny thing you can do. So we started with an optimization algorithm and converted it into an ODE. Now in today's lecture, we're going to talk about all kinds of different ODE solvers, right? Like different ways to solve this thing by discretizing time. You can plug any of those solvers back in to this ODE here and get an optimization tool for an objective function E. And in fact, there are all kinds of really clever ways to see how different ODE solvers correspond to different versions of gradient descent, which is kind of cool. There's a whole theory out there for that kind of thing. For those of you who are familiar with Nesterov and Atom and all these accelerated versions of gradient descent, there exist ODE versions of those too, and I will not drive them here because I don't remember how that works. Yes?
In practice, do optimization researchers often actually start with a gradient flow and then in real life derive new optimization algorithms by discretizing it, or is it always cutting back in that perspective?
You're saying like who came first,
Yeah, exactly.
the chicken or the ODE solver?
Right. Like, do you actually think of proximal methods as backward Euler for the gradient flow, or is that just convenient?
Ah, Chris, you destroyed my punchline. Do people? It's hard to say. I mean, I don't know which community came first, really. I'm guessing ODE solver has been around a lot longer because Newton's laws are kind of old.
Optimization researchers don't actually do this that much.
You know, it's usually, I think, more a lens of studying the convergence of an optimization procedure. Like, there's a lot known about performance of dynamical systems, and a little bit less known about a lot of these optimization algorithms. And so I think it's actually useful to kind of map it onto that space. I don't know which like I can't think of a good example where the insight came from this space first. Yeah. Right. So in any event, the point here is that you can use gradient descent as a model for optimization. It's perfectly reasonable. Sometimes people call this ODE, by the way, gradient flow. Although the more common version of gradient flow also takes E to be some function on a continuum. So for example, the gradient flow of the what's a good example? If I do gradient flow on surface area of a surface in 3D, that is something called mean curvature flow, which is an object that mathematicians care about. Okay, so right. For example, let's say that I want to solve AX equals B, our favorite problem in this class. Then now we can use the following ODE, which is, I guess, B minus AX as X prime, as some kind of model for solving these systems. And indeed, a lot of the iterations we'll derive here really will converge to solution. Any questions about that little link there? It's just to show you that, like, no matter what we do in this class, every single topic is linked together. Sorry. Now, of course, these days, ODEs happen on extremely ginormous levels. People use it for simulating turbulent fluids and physics and balls bouncing and things running into each other. Another great example that I really love from computer graphics domain is crowd simulation. So almost all of these movies these days that have like big crowds of orcs, which are the ones that are probably charging down a hill? Orcs? I thought an orc was like a sea creature. Okay, orcas. Well, maybe I have a crowd of orcas and they're charging down a hill. And now, you know, there are millions of them. I can't hire that many actors. Orcas are pretty fat, so I don't think I want to hire that many. They take up a lot of space. And so instead, I'm going to use my computer simulation to capture all of that motion. And many ways that people model this stuff is actually just with ODE solvers again. So they have the controls of the humans. They have some, you know, like targeted in mind, but also rules that's about collision, like how close they can get to one another. There's actually some weird version of physical dynamics that happens that's underlying a lot of these movie scenes. If I recall, what was the one with all the zombies that were like climbing over each other to like get over a wall a couple years ago, like 28 Days Later, one of those zombie films I think was state of the art in this kind of simulation, and had like, it's basically 100% computer generated. Incidentally, I'm supposed to emphasize in my teaching links to other disciplines that you may not expect. There's a really fascinating link to psychology that happens in this little corner of modeling, which I think is super cool. There's all kinds of interesting people out there that tried to write down differential equation models that really correlate with like how humans move in different spaces. I think this is so interesting and cool. And then they use the mathematics of like, you know, dynamical systems to like predict how people will behave in different situations. I can give you two examples that are kind of fun. Actually, our research group years ago was approached by people that were designing football stadiums. And there's a really interesting phenomenon. You may have heard of this. There's actually a death after COVID a couple years ago, where people were just like so excited to get back into the streets. There was some event in Korea that happened, and people flooded in so much that the streets were tightly packed with humans. And suddenly, like humans became a continuum, like waves and things started happening in this crowd. And there were actually differential equation models that simulate things like, you know, if I design a stadium and I put exits here, 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 and here, and there's a fire at this location, like where's going to be the points where people get jammed up, right? It's really a dynamical system. My favorite example of this is a SIGGRAPH paper from years ago, where they did all of these experiments where they had ordinary differential equations to predict motion of humans. So it was just like position and velocity of a little walking character in a virtual reality. And what they were trying to figure out was the effects of two people walking past each other in a hallway. I loved these experiments. They were so uncomfortable to watch. So they did all these experiments where like they'd have hallway of varying widths, and they'd have humans of varying widths, you know? And so you have two people, like one person going one way and one person going the other, walking past each other. And at some point, they're going to bump into each other on the shoulder. And the question is, how do they move to get out of the way? And there's so many different questions there. I mean, there's the dynamics of just who's the bigger person. There's a social effect, you know, like, you know, what do these people look like? Who are they? You know, who's the person that turns or defers? Do you turn in? Do you turn out? All these different questions. They did all these different experiments to try and kind of figure it out, and actually kind of distilled it into a differential equation model So like video games would have simulations of people walking through tight spaces that didn't look really awkward. And what was really fun is when they got it wrong, you'd watch it and something would just seem kind of off. Like people would walk past each other in a hallway and like kind of stare at the wall for a second or something, and it just looked really uncomfortable. But like rationally, it was perfectly fine. So anyway, ordinary differential equations don't just appear in physics, they appear everywhere. They're like a very typical model. And so one thing people will do is they'll write down one of these models, and then they're stuck trying to use these numerical tools to actually solve them, some of which are extremely challenging to apply. So hopefully I've convinced you, like ODEs are useful. This is the thing we care about. Now, one thing that is not terribly useful, I feel like usually when you take undergrad ODE class, the first 3 lectures go over all the motivation, and then for the rest of the end lectures of your course, you learn a bunch of magic tricks that were derived in the 1820s on how to solve these things by hand using fancy integration by parts. In my experience as basically an ODE expert, I've very rarely come across a case where I really needed whatever fancy integrating factor formula in my everyday life. But having numerical methods that actually solve these things, and by the way, having a theorem saying that they should have a solution is, in my mind, a very nice combination. Now, if we look at the mathematical theory of ODE, there are many different ways to classify these objects. And they vary in complexity. So here I've given you a bunch of examples of ODEs, and in kind of roughly in order of how annoying they are to solve. Certainly, I think by the time you get to the end of this list, I don't think you could solve these things in closed form. I say that, but now Harry's going to have a solution on this scrap paper in a moment. In the first one, we just have like y prime equals cosine of t plus 1. And I think we could all solve this thing by just integrating both sides with respect to t. That one's not so hard. And then we escalate from there. Like maybe y prime equals ay is now linear in y, right? So integrating both sides won't work, but that one does have a solution. We're going to derive it in a minute. Maybe it's the sum of a function of y and a function of t. Maybe there's multiple derivatives in y, like the second derivative and the fourth one here. Or maybe they're all like glued together and multiplied in some yucky nonlinear way, right? So this is like roughly the hierarchy of headache when it comes to ODE. Does that make sense? I think most of the tools that we'll derive today live in case number 4 here. So the fifth one is a bit of a less common situation where you've got some implicit function that defines y and its derivatives that does show up. And then essentially I think what people usually do is they use the root finding tools we talked about many weeks ago to isolate the highest derivative of y, and then just use the integrators we've already that we'll derive. So in order to exclude this very last case, we are going to consider ODEs that are what we call explicit, which in this case just means that we can isolate the highest order derivative from all the other ones, right? So here this is, so by the way, this upper parentheses k notation, I don't know if that's familiar to you guys, but this is the kth derivative in time t. Does that make sense? So this is going to be our problem. Our input is going to be a relationship that looks like this. So again, access to a function f, big F, and maybe its derivatives. And now we're trying to predict values of f forward in time given its value at time 0. Any questions so far about the setup of our problem? I want to make sure that this abstraction is reasonable before we go crazy solving ODEs. Okay, yeah. Right, so in the sort of most general version of ODE that we introduced at the beginning of the lecture, we just have 0 equals big F of all these things up to the kth derivative. So if you wanted to take one in that generic form and write it here, you need to basically isolate one of the derivatives, which is equivalent to root finding. Yeah. In that case, you can run it like, the good news is you can like get, solutions whose plot is like some S shape or something, which you can't really do here. The bad news is this like uniqueness becomes really hard to talk about. Okay. So the good news is that like this thing looks awfully complicated, and it would be really annoying for lecturers like me to have to carry around notation like this. And the good news is that there's a lot of tricks that we do in ODE to reduce to much, much simpler form and convince ourselves that we can basically consider a very simple version of an ODE without loss of generality. Right? And so in other words, we're going to develop a solver for a very specific first order ODE, and I'm going to argue that you can actually kind of use that solver to solve other stuff. It just doesn't look like it in the notation. This trick is called reduction to first order, and it's a fantastic way to write exam problems because it's very easy. And it looks a little something like this. So let's say that I have an ODE, which is the one that's on the screen here. So we have the kth derivative of f at t is equal to big F of t, f of t, fk minus 1. Okay. So for example, if I did f equals ma, right, then, by the way, that f stands for, I should say force equals mass times acceleration, since that f is not this f. If I just divided both sides by mass, then essentially the acceleration would be on one side and everything else would be on the other. Yeah? Okay. So it seems like we're going to have to develop ODE solvers that can cope with like juggling around a bunch of derivatives all at the same time, which is annoying. But we're going to use a trick that's going to allow us to do something a little bit different. Okay? So let's do an example first, and then maybe we'll generalize. So let's say that I have an ODE of the following form, like y double prime is equal to, I don't know, somebody call out an ODE for me. In other words, give me some expression in terms of t, y, and y prime. Don't all speak at once. Y prime plus t. How about sine y, just to add some nonlinearity for fun, without messing with Lipschitz. Okay, so this is an ODE you might want to solve. I don't know why, but it's probably fun. I don't know what the solutions look like. If you type it into Wolfram Alpha, I'm sure it'll make a plot for you really quick. But this is what we would call a second order ODE, meaning that the highest derivative you see in the expression is two derivatives in time, right? So this is what we call the second order. Notice f equals ma is also a second order ODE, so there actually are special solvers for such subjects. But now I'm going to make a really sneaky substitution here. So I'm going to define a new variable. We're going to call it v. And we're going to say that v is equal to y prime. Okay? Notice that this expression itself is like some kind of differential equation. Yeah? And in fact, what is v prime? Well, it's equal to y double prime, right? So, in particular, it's equal to y prime plus t sine y, which, well, y prime is v, so it's v plus t sine y. Okay? So far, it almost looks like it's like an inch away from being circular, but it's not circular yet. We're close. Does everybody understand what I did? Essentially, every time I see a y prime, I'm just substituting in a v. Cool? So let's summarize everything that we know about life. We have d over dt of vy is equal to something. Well, what's v prime equal to? It's equal to all this stuff, right? So v prime is equal to y double prime, which is v plus t sine y. What's y prime equal to? Well, it's equal to v. By the way, usually you write them in the reverse order. I don't know why I wrote it this way. But, you know, such is life. Does everybody understand why this expression is equivalent to this one here? All we did was we introduced a second variable, which was the first derivative of y. Oh, I'll pause for a second. Now, here's the thing. This thing in itself is an ordinary differential equation. Notice that there used to be one variable as a function of time. Now there's two, v and y. But in exchange for that, how many derivatives are in this expression? One. Right? There's not, like we started with a second order ODE. What is this thing? This is first order. So in other words, essentially what I'm demonstrating for you is that we can make an exchange. We can exchange derivatives in time for additional variables in our problem. Does that make sense? Any questions about this trick? So we have this in more generality on the screen here. I'm not going to write it out because it's annoying. But here's the basic idea. I'm going to define a bunch of functions f sub I. I'm going to look at my phone and make sure I don't know who keeps calling me. Where fi is basically the ith derivative of the original function f naught, right? So for example, and now look at this ODE here. What is it saying? It's saying the derivative of f naught is f1, derivative of f1 is f2, derivative of f2 is whatever. And then I take my final expression, the derivative of fk minus 1. Well, that's the kth derivative of f, which is what we started with, right? But now on the right-hand side of our ODE, every time we see like f prime, we put f1, f double prime, we put f2, and so on. So this expression on the bottom of the slide is a first-order ODE. You see that? We started with a kth order one, and we ended with a first-order one with k times as many variables. Does everybody understand this trick? This is just basically like notation in a sense. So what does this mean? Do I ever have to solve ordinary differential equations? Like, do I need an algorithm specifically for ordinary differential equations with like 3 time derivatives? The answer is no, because I can just use a method for things with 1 time derivative and just introduce more variables. Now, this is sufficient, but it's not necessary. There do exist special solvers for things with 2 time variables, and they can often behave better than the generic stuff. But we'll deal with that in the next lecture. And by the way, it totally makes sense, at least for k equals 2, to have a special solver, because again, f equals ma is an extremely important equation, and if you can like squeeze some other accuracy out of that one specifically, it's worthwhile to consider. Okay. In the slides, we do another example here. So for instance, if I wanted y triple prime equals 3y double prime minus 2y prime plus y, notice that I can introduce z and w as the first and second derivatives of y, respectively. Right, so notice that the first row of this equation is just saying y prime equals z. The second one is saying z prime equals w, right? And the third one is the original ODE. So this is just a standard trick. By the way, notice what is the form of the matrix in this problem? It's always going to be like identity shifted by 1. Yes? Yeah, it's always the structure. So it's identity shifted by 1 with zeros, and then the last row is all the other stuff. Yeah. I'm not sure that actually helps you compute the matrix exponential of this thing, which is what you would need in ODE, but it is true, that's the form. Okay, so what have we argued? We've argued that, like, at least in our intro lecture to ODE, if we can come up with solvers that only deal with k equals 1, we're actually still kind of okay, right? We still have a solver for the generic ODE that we set out to solve. And in fact, we can do a little bit better than that. So here's one that I think is, it's funny because these tricks, there's so many like stupid math tricks that are annoying. They're like mathematicians being smartasses and like subbing in like things that feel kind of tautological. We can also do that with t dependence as well. So in particular, here's 2 different types of ODEs. Here's a time independent one and a time dependent one. Notice, by the way, have you guys seen this kind of visualization before? This is called a slope field. Remember that like we have, in this case, this would be an ODE that looks like y prime equals f of t comma y, like that, right? So essentially for every point in the t comma y plane, there's like a little slope that's telling you how y should change at that location. And so that's what this thing is visualizing. That's like what our ODE integrator is doing. Right? So in time-independent ones, what we say is that f does not need t as an input. Right? And so that looks like the case on the left-hand side. Notice that the little slopes are the same as I move horizontally. Yeah? Whereas time-dependent ODE, these things can change the function of t. Everybody understand this picture? You're all so quiet. It makes me very suspicious. Yes? That's right. Exactly. Right. So if you fix a t, there's interesting stuff happening in the y direction, right? So I think it's correct, right? So it's a function of just y, not t. Yeah, it's easy to get this one backward.
Everything's constant along vertical lines.
No, everything is constant along horizontal lines.
Oh, right.
Yeah. Right. For every vertical line, you have an interesting function, and it's the same interesting function. Yeah. Any other questions? It's very easy to get these visualizations wrong. Okay. Sometimes for time-independent ODE, we give this a special name. We call this an autonomous ODE. Now, essentially what I'm doing before we even talk about numerical methods is we're just like trying to reduce the space of numerical methods we're going to have to derive, right? That's essentially what I'm after here. So far, we've managed to say like, no, it's fine to just put 1 here, right? And in fact, I claim that it is enough to only consider autonomous ODE using a similar trick. Anybody have any suggestions? How am I going to go about this? I'm going to slowly erase the board so you all can think of your clever math trick for reducing to an autonomous ODE. Different from an autonomous robot, by the way, in case you're wondering. I'll give you a hint. What is d over dt of t? Thank you, Axel. It's 1. That's exactly right. So here's my sneaky thing that I'm going to do. So let's say that I have, I have y prime is equal to big F of t comma y, like that, right? Well, one thing that I could do is the following. I could say, okay, I'm going to have d over dt of, and maybe I'll make a new variable. So I'm going to say y and then maybe z, okay? Z is going to be time. So we're going to say, well, dz dt is just equal to 1. So in other words, z of t is going to be equal to t. Do you see that? Because it has a slope of 1. And now we have is equal to f of z1. So this object is an autonomous ODE, right? This vector here is a function of our unknown function of time, which is now y comma z. Make sense? So again, notice that all of these tricks, they have the same, or here's the same trick in slightly different notation, by the way. The basic trick is that we exchange more dimensions in our unknown function for derivatives and time dependence and all this other stuff. Yeah. So there's like a conservation of computational headache, like you haven't somehow reduced the storage that you need or something like that. But in terms of the algorithms we derive, we can sort of just consider ODE of the form at the top of the slide and know in the back of our head that we can actually apply it to other stuff. Yes? Yes. Sad. Yeah. I mean, this one not so much, because it turns out that like differentiating 1 with respect to time is a pretty easy thing to do. Yeah. In fact, I don't think solvers really do this one, by the way. Like, this is more of just a notational thing. Like, in reality, it's really not so hard to handle. Usually so Harry's question is whether tricks like this affect stability. The answer is yes. I'd say they affect it, and they affect it in some really strange ways. I mean, you have to think about like all the different dimensions of this thing all being stable at once, right? So it could easily be the case that I need to use like higher quality integrators for different slots of my vector, for example. We're not going to talk about that here, but yeah. So one thing that's just worth noting, by the way, is that there are so many different ways to visualize ODE. And the reason for this, one, is that physicists they don't have much to do with their time, and they like to come up with ways to draw pictures. The other is that like really, it's really hard to come up with like ways to visualize differential equations bigger than 1 dimension. I mean, so far, like for instance, the slope field that we saw before, notice that like y is a 1 variable function. Like y of t is a single value, right? It's not even a vector. If you want to at least lift into 2 vector, like for instance, a second order ODE, one way that you can do that is by visualizing what we call phase space. I don't know if anybody's ever encountered this. So if you've taken a physics class, you've probably seen diagrams that look like this one. So this is used for single variable functions that are maybe but maybe you're considering a second order ODE. So in this case, what do? So here's a second order ODE, y double prime equals minus sine of y. And now I simulate this as a function of time. This traces out some path in theta, comma, theta prime, comma, theta double prime space. So it's like a little path in that space. And then all this is like the traces, right? So the horizontal axis is like position in this case, and the vertical axis is like velocity. Now, anybody, your fun trivia question. Anybody recognize this ODE? The pendulum, right? Like if you think about it, so when theta is like, so remember sine of theta is roughly equal to theta for small thetas. So when theta is like slightly positive, this thing pushes it backward, right? When theta is slightly negative, it pushes it forward. This is the ODE of a pendulum swinging. The sine of theta comes from the fact that, like, you know, if you have a pendulum of some mass is swinging like that, then the force that's affecting the theta here is just the projection of this onto, you know, the horizontal line here, for example, for the horizontal position. So from this phase space visualization, we can kind of see what's going on. So let's say that I give my pendulum just a little flick, right? So it's just kind of spinning back, you know, it's just swinging back and forth like that. But then that's actually tracing out the loops in this phase space, right? So it's like moving to the right with positive velocity, and then to the left with negative velocity, to the right, to the left, and so on. Notice that this does not show the t dependence in this plot, unlike the one we showed before. And then if I whack my pendulum really hard, it's just spinning around more and more and more, and now I end up in these traces down on the bottom where the angle just keeps accumulating. It never reverses direction. Yes? Yes, although from this diagram, you don't necessarily know that. Yeah. Mm-hmm. Yeah, that's right. But like this is a very special picture where these loops close up. You know, like a lot of physical systems don't have that problem. Okay. Essentially, there's so many ways to visualize ODE. If I have ODE with more than one component in my vector, like for example, this is an extremely famous ODE for a function xyz of t. Does anybody know what this thing's called? This is called the Lorenz attractor. This is, in this case, I believe, just a first order ODE, but it's a really complicated one. So all I can do here is just draw the paths, right? There's no t dependence, no velocity, no nothing. Like this is just showing where particles move in xyz. Yeah? These are our common visualizations. Again, that's slope field, which is all that can show is a first order ODE of a single variable. There's phase space, which can show a second order ODE of a single variable. And then there's just visualizing the traces, which can show a higher order ODE of 3 variables, but doesn't actually show you anything about dependence on time, right? This is just showing you kind of where the particle went. Incidentally, so you guys all have heard of Lorenz attractor. Do you know where it comes from? Yeah, it's a weather model. So apparently there are these weather models where your weather's in like kind of a stable state, and then like something happens, it spirals into a particular position, and then it'll like jump to some other stable state and like be over there for a while. And actually the early history of numerical methods were tangled up with the study of this ODE and many others, right? So I believe the Lorenz attractor was one of the first ODEs that was like computationally numerically integrated back in the day. They got a plot that looked like that. They thought, oh, this must be a bug with my numerical integrator. In this case, that was not the case. It turns out it's just a really complicated differential equation. Notice that like you have wildly complicated traces for your ODE, and this is a very simple equation to write down, right? So it's not hard to come up with really complicated examples of differential equations you want to solve. Okay, so the last little theoretical thing that we should address is to make sure before we go about solving ODEs that like they actually have a solution. So for example, it's actually kind of hard to cook up an ODE that doesn't, but you can. And here's the one that I came up with, which is dy dt equals 2y over t. Let's see what happens if we try to solve this thing just for fun. This is also a good review of your like AP calculus skills from high school, like magic tricks for solving differential equations of very specific forms. This is one of them because it's separable. Right, so we have dy dt equals 2y over t. Maybe you have any suggestions? How would I go about solving this thing? You guys remember like these stupid calculus tricks? Axel's like, hell no. First of all, you might think like, well, why is this thing well defined? Like I'm dividing by t, right? But it's actually a reasonable ODE to solve because do I actually need dy dt? Like, do I need this at t equals 0 necessarily? No, because I know the value of y at 0, right? So I only need the slope infinitesimally close to 0. A little weird, but it is the case. So here's the thing that I can do. I can multiply both sides by t, so I get t dy dt equals, in fact, maybe I'll add a little space here, equals 2y, like that. And now I'm going to integrate. Oh, I'm sorry. That was dumb. That was the opposite of what I wanted to do. Sorry. I want to do the following, which is 1 over y dy dt equals 1 over t dt. Okay, that makes more sense. Not dt, just 1 over t. 2 over t. Oh my god, I'm sorry. Your instructor's a hot mess. There we go. Do we all agree that in try number 5, I managed to multiply both sides by one number? Okay. You can, at this point, you guys probably have a pretty good kind of Bayesian model for how much sleep your instructor has gotten lately. It tends to be correlated with NSF grant deadlines. Okay, so how should I now solve my ODE? Any idea? I kind of anticipated it by accident. Well, I could integrate both sides dt like that. Yeah. So what's the integral of 2 over t dt? 2, maybe we'll even do natural log of t. Let's only worry about positive t. Okay. What is the integral of 1 over y? Notice that we have dy over dt and dt. So by integral change of variables, I can kind of cancel those guys. So this ends up being natural log of absolute value of y here, right? So if I exponentiate both sides, what I conclude is that y equals some constant times e to the t squared. Make sense? Let me check my notes to make sure that I agree with that. Yeah. Okay. Now remember how I posed. Wait. There's no Oh, sorry. If I exponentiate both sides of this, I just get t squared, obviously. E to the natural log of so this 2 natural log of t is the same as natural log of t squared. When I exponentiate that, I get ct squared. See, I can write pretty much just total garbage on this board, and you guys will just happily nod along with it. You're killing me. Okay, so remember our ODE problem. What do we specify? We specify, in this case, it's a first order ODE. So the first thing that we do is we give it a relationship, like this one here. Great, check. The other thing that we have to do is give it dy dt at 0, right? And then the ODE problem says, given these 2 pieces of information, predict the value as a function of time. Yeah? Now, despite your instructor's embarrassing series of high school calculus mistakes, we did eventually converge on what I believe is actually the solution of this problem. Do you guys spot an issue here at t equals 0? Let me ask a question that I know you're equipped to answer. What is the derivative of this function with respect to t? One more time. Louder for the people in the back. Everybody on 3. 1, 2, 3. What is the derivative of this function? Okay, now this time with the people that didn't talk. What is the derivative of this function? Now it's just Chris. I don't know how that converts. Okay, so y prime, again, is equal to 2 times c times t. Oh my god, you're killing me. So in particular, what is y prime of 0? 0. Wait a second. I said that my input data was this thing. Well, that's a contradiction. So what we showed is if I satisfy this ODE, then I take this form for some c, but that implies a particular initial condition. So this ODE is unsolvable if I give any initial condition other than this one. Moreover, when I give this initial condition, it turns out any choice of c gives me a solution to the original problem. This is a really weird differential equation. I encourage you to plot it in like Wolfram Alpha. Like it is perfectly like solvable as long as you're careful. Okay, and so yeah, I mean, if you think about it, what do the traces of this thing look like? Well, they're basically just multiples of t squared, right? So they're like this all the way straight up. I mean, they cover the entire region here, and similarly down. Yeah. Okay. Whew. So does everybody agree then that like, if I just give you something of this form, I need to be careful to make sure that it actually has a solution. That's my point. Yeah? But the good news for us is that there are extremely generic conditions under which there exists a solution, and it is unique for an ODE. So here's one of the more common ones. Suppose I have an autonomous ODE, and it is Lipschitz, which is a property we have covered in this class. Then we're good. There's exactly one solution, and it exists for all positive t. Okay? And I believe even for non-Lipschitz, like locally Lipschitz or something like that is probably enough. I'd have to think about it. Okay. So finally, I think we've sort of finished our discussion of sort of general theory and kind of at least understand the basic universe. Any questions so far? It's so quiet today. I think it's because it's dark out at like 3 p.m. Is that what it is? You guys are even less engaged than normal. Okay, so right. So there's one additional thing that we should do. There's a very common thing that people do in the theory of differential equation, which is that they use something called a model equation to kind of understand how the different solving algorithms that we derive are going to behave. What that means is that we're going to have like the world's simplest ODE of the form that we've decided we can work with. And then we're going to kind of say, as we apply our algorithm to this really simple ODE, we're going to be able to understand in closed form what it does. And that's going to give us a little bit of insight into the more general behavior. And in particular, we can apply a Taylor series. Shocking, right? And so let's do it as follows. And in fact, we'll simplify our problem even more and do it just in one dimension. So like here, y is a single value as a function of t. Doing it in multiple dimensions isn't really any harder, but we can, just for simplicity of notation. So let's say that I have a function y prime equals f of y. Well, if we're looking for just like a generic way to understand this for like the behavior numerical method, we might kind of approximate f with like a very simple thing, like a plus b times y, right? Like use a Taylor series for f or some other thing. And that's not to say that this is an interesting ODE to solve. In fact, actually, by the way, I'm going to switch my notation ever so slightly just to agree with the book. Let's do AY plus B. But all this is this is a specific ODE, but we can kind of use solutions of this equation as a lens for understanding. Like we can write down the actual solution of this thing, write down what our solution algorithms predict, and see how well they agree, right? So this gives us a very concrete way to kind of understand behavior of an ODE solver. Okay? And the way to obtain this really is to think of like, well, at least for small y, this is some kind of Taylor series equivalent, right? That's all that's really going on here. So the first thing that we can do, if you've ever taken an ODE class in the past, by the way, I think very typically you see the model ODE is just this, like f of y is equal to ay. A very common thing to be kind of presented with. So the first question is like, well, wait a second. If we want to think about Taylor series, we probably want a constant term. And so the question is, well, why can we kind of eliminate this this object? And so here's a little sneaky trick. Let's define y bar is equal to y. I forget if it's minus or plus b over a. So in other words, we're just going to take a constant shift of our unknown function. So what is y bar prime? Well, b over a is a constant, so this is just y prime, which we know is equal to a y plus b, like that. And what is y? Well, y is equal to y bar minus b over a plus b. So these two guys cancel, and we get a y bar. And this is why the typical model ODE kind of just crosses out b and puts 0, because it turns out that the constant term, sometimes we call this the inhomogeneous term, really doesn't do anything interesting to this equation. It just shifts it. Does that make sense? Okay, so right, so this is our sort of setup. We linearize our problem with a bit of shifting of variables. We have y prime equals ay, which is sort of the simplest possible differential equation you might want to solve You probably wouldn't solve this numerically, by the way. That would be kind of dumb because we know the solution to this ODE. But this is just to say that like this is an ODE whose solution we know, so we can compare all of our algorithms to the actual solution and perfectly evaluate our error. That's my point. Okay? Now, this is the phrase that we often have for this is called the model equation. This is a thing you guys have encountered before. It shows up in ODE theory sometimes. Yeah. And it's basically just a linearization of ODE theory. That's all that's going on here. Now, I managed to embarrass myself solving that more complicated ODE, so I suppose I should redeem myself by solving the model equation and showing that indeed your instructor is capable of high school calculus, which is probably a mistake. So let's say that I have dy dt is equal to a times y, like that. How do I solve this thing? Well, once again, I can divide both sides by y, at least skipping the y equals 0 case for now. Right, so now I have 1 over y dy dt is equal to a. If I integrate both sides with respect to t, I'll get log of y is equal to at plus the constant. Right? So when I exponentiate both sides, I get y is equal to a different constant, times e to the at. This time I did it right, I think. I hope you're all impressed. Cool. Okay, so lucky for me, that's on the slide here too, and I believe is an example you've probably all seen 100 times. Okay, so the first thing to do is to think a little bit qualitatively about this, this problem here. In particular, I claim there's sort of 3 regimes that are defined by the constant a. Yeah? And unsurprisingly, this is when a is negative, when a is positive, and when a is equal to 0. So here's what the solutions look like. Visualize as a slope field. So when a is positive, what happens to e to the at as a function of t? Yeah, it gets hella big, right? And so in particular, we're in the case on the left-hand side, right? The solutions diverge. Notice from a numerical perspective, that's going to be a really big problem, right? Because like, if I get my initial conditions a little bit wrong, that error is going to amplify as a function of time. Okay, the a equals 0 case, my solution is now just a straight line. And if a is less than 0, what happens to my solution as a function of time? Yeah, it goes to 0, right? Okay. So the terminology that we're going to introduce here is that this ODE is stable when a is less than or equal to 0. And in fact, the solutions get closer to one another when a is less than 0. Do you see that? Like the initial conditions kind of compress as a function of time. And when a is bigger than 0, it's unstable, right? So like when I have a mistake in my initial conditions for my physical system, they get amplified as a function of time. So let's actually visualize what this looks like. So in a stable ODE, I'm in the left-hand side. I can look at, like, let's say that I make a mistake in y of 0. So like maybe instead of the first point, I got the second point here. And now I solve the ODE with these 2 initial conditions. Notice over time, they actually kind of get closer and closer to one another. Whereas on the right-hand side, if I make a small mistake, it gets amplified as a function of time. So which of these 2 regimes do we kind of hope that the equations we want to solve fall into? Stable, yeah. In fact, I think some people would argue that like, trying to solve an unstable ODE is ill-posed, certainly for large t. Okay? One thing that's done in the textbook, I think we'll skip here because it's not terribly exciting, is what happens when I have the model equation, but instead of just in one variable, now it's in multiple variables. So now y is a function of t still, but it's a function that outputs like n things instead of one thing, right? So now it's y prime equals ay, where a is a matrix. Then essentially what you get is still this expression, but e to the at is replaced with the matrix exponential, if that's the thing you're familiar with, which basically exponentiates the eigenvalues. What does that mean? That means your multi-dimensional ODE is stable exactly when A has eigenvalues that are all negative. Yeah. If that's not familiar language for you, I'll let you read the book chapter on that. I should be doing that more often. I have a feeling none of you guys are actually opening the book. Okay. So with that, finally, we have concluded our sort of theoretical story about differential equations. We are equipped to start solving these things with algorithms. Any questions so far about like what the heck is this problem we're solving and why would we solve it? then we'll proceed. Okay, so what we're going to cover for this lecture and the next one, and possibly the lecture after that, are algorithms for what we would call numerical integration of ODEs. Notice this is different than numerical integration like quadrature, ever so slightly from our previous lecture. Here what we mean is like we're given y at tk, and now we'd like to produce y at tk plus h, or something like that. Like we want to increment time a little bit forward, given the state at a given time. Yep. And given all the reductions that we've done in the past several slides, it's enough to just consider this autonomous first-order ODE that we've written here. So at the end of the day, we're given access to this function big F, and we're asked to integrate it. Questions so far? About like the problem we're trying to solve? Now, I think we could all derive an algorithm pretty easily. In fact, I think if I gave you an ODE and you got on your computer and I gave you 20 seconds to code something, I bet you could do it. And what would I do? Well, let's see. So I have dy over dt is equal to big F of y, like that. Well, one thing that I can do in kind of quotation marks is the following. Well, I can multiply both sides to get dy is equal to f of y dt. This is, of course, meaningless mathematically, right? But it suggests a very simple algorithm, right? It suggests a technique that looks something like the following, that I'm going to get the y at k plus 1. By the way, I'm going to use this to say like the number of steps of my integrator. So like a subscript of k plus 1 is going to mean that I integrate, and we're going to use the letter h to denote like the amount of time in between each of these things. So we can say dy, so we're going to say, well, y plus dy, right? So that's going to be yk plus the dt, which is h, times f at yk. Does that make sense? So, anybody know the name of this thing? This is an algorithm. This is perfectly reasonable. Forward Euler. That's right. Now, the way that I wrote it down here feels kind of heuristic. I mean, like, I have to put this thing in quotation marks because there's like a dt hanging there. So let's derive it in an ever so slightly more rigorous fashion. In particular, here's one thing that we can do. Notice that by definition, if I take f and I evaluate it at yk, right, the ODE says that that's y prime at time k, like that, right? That's the definition of the ODE. But remember from our previous lecture, well, what is this thing equal to? Well, it's equal to yk plus 1 minus yk over h plus big O of h, right? So in particular, if I multiply both sides by h, I isolate a little bit. Notice that I'll basically get the forward Euler integrator. I'll get yk plus 1 equal to yk plus h f of yk plus big O of h squared, like that. So now I even know, like, this is the amount that I've lost in error when I truncate by just having those two terms, and this is the forward Euler integrator. Does that make sense? Now here's a bit of a conundrum. This has to do with actually our strategies for quadrature. We often say that forward Euler is first order accurate. Now that feels like a contradiction because I just put an h squared here. Does anybody understand what's wrong? Yeah. So here's the thing. If I make h smaller, yk plus 1 is now like a different time. Do you see that? Like now time is advanced by less amount, right? So let's say that the task here is to predict like y at time 1, right? Then how many steps? If I have a time step of h, then the number of steps is roughly the amount of time I want to advance divided by the size of a single step, which is 1 over h. Right? So if I want y of 1, then I have to do 1 over h number of steps roughly of my integrator, each of which incurs h squared error. So it's the product of these two things that matters, and that's what makes it first order accurate. Does that make sense? Any questions so far? Okay. In fact, in slightly more precise error, the forward Euler has what we call h squared localized truncation error, and then h global truncation error, and then the phrase that people use is that it's first order accurate. Okay? Now, this is going to be the first time that we use our model equation. Ta-da! And that's so that we can understand the behavior of this thing. So let's say that I want to do y prime equals ay. And again, this is not like a clever algorithm for actually solving this ODE. This is purely a theoretical study. So again, remember our model equation is like that. Right? So what is forward Euler going to want to do? It's going to say yk plus 1 is equal to yk plus ayk times h. That makes sense? Specifically for this ODE, if I were to apply that method to it. So we can factor this ever so slightly. This is 1 plus a times h times yk. Everybody agree with me, specifically for this thing? So in other words, if we kind of accumulate steps together, we can say that yk is equal to 1 plus ah to the k times y0. Incidentally, if you kind of squint, this actually does give you an algorithm for approximating e to the at, but I'll let you think about that. So let's assume a is less than 0, because that's the sort of favorable case for numerical solver. That's the stable one. What is this saying? This saying that really, when I advance this thing by a time step, all I'm doing is just multiplying by a constant. Huh? So what is this constant? Well, let's say that h is pretty close to 0, like it's a very small positive number, right? So we have a is negative and h is a very small positive thing. So this is 1 minus like epsilon. Yeah. So what is this number? It's like somewhere between 0 and 1, right? So in that case, what happens as k gets big? Goes to 0. Now, let's say that h, right? So in particular, here's a way to draw this. So let's say that h is less than 1, I think is a typical way to write it, right? Then if you think about it, the iterates of this thing just kind of decay to 0, which is a good thing. I mean, that's what you would expect for this ODE, right? Now, let's say that h starts to get a little bigger. In other words, like I get greedy with my numerical ODE solver. You see that? Like essentially what I'm saying is I want to just like take one step and guess like the future really far ahead. That's what big H is saying. Okay? Eventually, what's going to happen? So A is negative, right? So let's say that H kind of starts getting bigger than 1 over A. Right? So what happens when H is bigger than 1 over A? Well, now what is this whole expression? It's actually negative. Do you see that? So what is my ODE solver? Well, if H is on the order of 1 over A, then maybe it'll kind of start doing one of these things. Right? So this is like H is on the order of 1 over A. And then eventually, H is big. This becomes a negative thing. It becomes so negative that it actually becomes bigger than -1, and it spirals out of control. Yeah? Everybody understand this picture? Which of these three things looks like the way that the solution we want? The top one. That's right. This is what we call stable. Now, this is an overloaded piece of terminology, this word stable. We've used it twice, right? For one, there's the ODE itself, which is stable when A is negative. But notice that even when A is negative, our solver can still blow up in this third case, right? It can still diverge rather than go to 0, which is what we would expect. In this case, we would say the ODE is stable, but the integrator is not. That make sense? Okay. Here's a nicer picture of what this looks like. Essentially, all we've done is just scale. Notice, by the way, you can equivalently scale A or H, right? It's the same thing. Okay. Right. So in fact, if you work this out more carefully, kind of like we did, this is stable as long as H is less than 2 over the absolute value of A. Notice that 2 happens because this case is still stable. It's ugly, but it's stable. Right? It's still converging to 0. That's where that factor of 2 comes from. Okay? So this is our first example of something that we're going to see a lot in today's lecture and next time. This is called a time step restriction. Okay? And it is the bane of people that solve ordinary differential equations. Because essentially what it says is that, like, if I get too greedy with h, it's not just that my approximation is bad, it's that my approximation explodes. Right? So if I'm making a video game, for example, I might not care so much if the physics is correct. But what I do care about is that, like, things don't blow up in the user's face. You know, like maybe it's a kid's game and they're swinging on the swing. If I'm like on a swing and slowly the swing starts picking up energy and just spinning around, that would be a pretty crazy video game. And that really is what will happen if you use like forward Euler in a simulation like that. So now we're going to derive all kinds of other ODE integrators with all kinds of other properties. And the really annoying thing here is that there really is no free lunch. Like these are all different trade-offs. This is a big space in engineering. Like some of them are going to be accurate but unstable. Some of them are going to be stable but accurate. Some of them are going to be computationally efficient. Some of them are going to be computationally slow. There's like this giant constellation of different objectives in this space. Okay. So you might notice that I call the algorithm that we just derived forward Euler. What do you think is going to be the next algorithm we derive? Backward Euler. Thank you. So let's go back to our previous board here. So here's the thing. Notice this is a first order approximation, right? So I could have just as easily done the following. Well, notice that, like, if I put a k plus 1 y prime here, right? Then, and I use backward divided differences, then the expression I just wrote here on the board, or edited rather, is still true, right? This is still true up to big O of h. So in other words, if I rearrange, I have the expression at the bottom of the board. Okay? Sneaky, huh? It's almost like I left it there on purpose. So if I take just this expression here, this thing is now called the backward Euler integrator. Let's also put it on the screen just for cleanliness. Notice that, by the way, our proof for truncation error is identical in this case, right? Like nothing has changed. Yeah, so we call backward Euler a first order accurate method. Now, you might notice a weird thing about backward Euler. What are we trying to do? We're trying to take yk and then predict yk plus 1. Right? That's really what all these integrators are doing. Notice that yk plus 1 is in two places in this expression, right? This is a system of equations. So in order to advance time by time step h, I'm going to actually have to solve this thing using a root finding tool like Newton's method. Right? Do you see that? Like I've got to resolve this thing to find yk plus 1. Any questions so far? We're going to do an example in a second. Yeah. Oh, sure. Well, take a look at it. The proof actually doesn't change. So notice that here's our ODE, right? So y prime k plus 1 is equal to f of yk plus 1. This is just the ODE. And now, when I do divided differences, I can choose to do them in a positive h direction or a minus h direction. Those are both first order accurate estimates of the derivative at that time, right? So here, this is the backward looking divided difference from k plus 1 to k. Yeah, and that still gives me order h error, and then the backward Euler is just a rearrangement of that expression. Yeah. You can guess what we're going to do next. Is average those two things, right? Do trapezoid method. Okay, but it looks like we're low on time. This is great. I've been moving slowly for once. Okay, so let's go back to our model equation. So, sadly for us, this entire picture changes. So the backward Euler method, again, it doesn't actually give you a formula for the next time step. It tells you a system of equations you have to solve for the next time step. So let's say that we're considering y prime equals ay. So now we have y k plus 1 is equal to y k plus, I guess, a y k plus 1 times h, sorry, like that. All right, so this is like what the backward Euler thing would want to solve for our ODE. Now, luckily for us, because this is linear, we can actually just solve this thing, right? So in particular, notice that I can subtract off h times a times yk plus 1 from both sides. So in other words, I get 1 minus h times a yk plus 1 is equal to yk, right? So in other words, I don't know why I'm like taking this chalk to the tiniest possible nub, but I'm committed now. Yk plus 1 is equal to 1 over 1 minus h times a times yk. That makes sense? Okay. So finally, we've concluded that yk is equal to 1 over 1 minus h times a to the k times y0. Again, we would never do this in practice. This is just a way to understand the behavior of our integrator. Yeah? These are two different first-order estimates. So these are both estimates that hold to the same level of accuracy. The question is, why might we use one or the other? Well, why might we not want to use backward Euler is that we have a system of equations to solve. I mean, it's pretty easy when it's one-dimensional and linear. It's not going to be so easy when it's like some weird nonlinear thing, like if I had cosine of yk plus 1 in there, right? On the other hand, let's take a look at this quantity, 1 minus h times a. And let's again consider the case a is less than 0, because remember, that's the interesting stable case. Otherwise, everything explodes anyway. So h is positive and a is negative. So what can we say about this quantity 1 over 1 minus ha? First of all, what is the product of ha? Is it positive or negative? Negative. So what's minus ha? Positive. So this is 1 plus something. Yeah? So 1 over 1 plus a positive thing is going to be between 0 and 1, right? So notice that this number necessarily is somewhere between 0 and 1. Yeah? So what we derived is essentially a really interesting picture for forward Euler. Looks something like this, which is I can put a ginormous h into forward Euler. I can make it as big as I want, and it will remain stable. In other words, like I can forward integrate and never have my solution explode, so long as a is negative. Backward Euler. Thank you. Also backward Euler. I'm sorry. Somebody please message me, and I'll fix that in the slides. Yeah, let's just say backward Euler stability. That's embarrassing. Okay? So let's make it go away. This is what we showed. So in other words, what we showed is that backward Euler, my apologies, is unconditionally stable. But here's the thing. What's the accuracy? It's still big O of h. So we can put a gigantic h in here and it'll give you something and it won't explode. But that doesn't mean that it has anything to do with the physical system that you're trying to approximate. It just means it doesn't explode. Right? And in fact, the accuracy of this thing is the same as the accuracy of forward Euler. So in other words, so let's think for a minute, if we're engineers, you know, we have two different options. We can do negative h or positive, or sorry, we can do forward or backward Euler. Yeah. What should be your advice? Like, give me a rule here. Like, when should I use forward or backward Euler if those are my only two options? Let's say that I want a really accurate solution, so I'm going to take really tiny steps h. You probably want to use forward Euler. Why is that? Like, computationally, it's a lot less expensive, right? In fact, so for instance, actually in the next slide here, let's say I have y prime equals ay, but y is now vector valued. Then I've written the expressions here. They're derived in the book. Maybe we'll start with that next time. Notice that one of these involves a matrix inverse, and one of them is just a multiplier. Yeah? So if I'm going to use little tiny steps h, and they're both accurate anyway, and they're both stable for small h, then I might as well use forward Euler because the computational expense is really small. Now, maybe I'm engineering a computer graphics system. I want to take big steps h because like I don't got all the time in the world and I don't care about accuracy all that much. Then which of these integrators should I probably use? Backward Euler. Thank you, Axel, for putting your instructor out of his misery. Backward Euler, and why is that? Well, I can take as big h as I want, and this thing will never blow up. It might not be accurate, but at least it's not going to give me like something that just looks really terrible. That make sense? So for example, a typical example of a really nasty ODE to solve is cloth simulation. This was actually like back a million years ago when I was lucky enough to get a job at Pixar. There was this little scene where what's his name, Linguini, was running around the kitchen. He was wearing a frock and like chopping the food, and the rat was controlling his kitchen knife or whatever in Ratatouille. And they had this interesting little bug where like slowly throughout the scene, Linguini's frock would just kind of lift off. And the basic issue here was sort of twofold. One is they were using backward Euler style integrator, which they had to do because this is a really dynamic system. There's like stuff flying every which way, and it's very easy to get instability. So in other words, the time step restriction, notice that it's a function of a, so like, and remember a, it's like e to the at, so it's like sort of the rate at which things blow up. So there the a is probably really big. So in that situation, like the matrices were really close to singular. This was a crazy looking problem. They're using backward Euler. And moreover, they were using conjugate gradient to solve that linear system. They just weren't running it to convergence. So it was an interesting kind of combination of the stuff we've covered in this class. So anyway, so cloth simulation is a very typical application where backward Euler is typically the choice because it's extremely unstable. It's like this giant network of springs in effect, which is kind of holding the cloth together. And those are hard things to resolve. Whereas like very easy ODE tend to be things that are very smooth and kind of glorpy, then the forward Euler things are okay. Okay, fantastic. Well, I think that's a good whirlwind introduction to the basics of ODE. In our next lecture, we're going to go hog wild, and we are just going to like derive a million different integrators with all different kind of trade-off between accuracy, stability, and computational effort. We're also going to ask a very reasonable question, which I think is not asked in most numerical analysis classes, which I find to be preposterous, which is we spend so much time talking about the model equation, but we know how to solve the model equation. And yet, all of the integrators we write down get it wrong, right? So like the one ODE that we actually know how to solve is somehow not built into our integrators. So my question for you guys to think about for next time is, how might I actually build in? Like if I know e to the at is the solution to this thing, and moreover, like linearizing stuff is very common, how could I use that to my advantage? And that's going to lead to a very advanced integrator called an exponential integrator. Spoiler alert. Okay. So with that, I will see you next time. I think our plan for our next 2 lectures is as follows. The next lecture, we're going to cover advanced integration methods. We're going to get all the way to RK integrators, which are the standard in computer graphics and simulation. And we'll talk about some really fancy implicit integrators and exponential integrators and so on. And then in our final lecture, we're going to talk about the adjoint method, which is how to differentiate through solutions to an ODE, which is used in optimal control and also in neural ODE, which is a fun application to end with in this class. Okay, so with that, I will see you next time. Have a fantastic, whatever day this is.